Let's continue with the chapter 17 practice problems. Let's do number 9. So in this problem, we have 4 charges, and we have that they're arranged in a square, so the distance between all of them is 1 meter. B and C are opposite corners. A and D have a charge of negative 0.35 coulombs. And B and C have the charge of 1 coulomb that's already drawn on the paper there. What's the magnitude of the force on charge B? So we'll just call all these charges QA, QB, QC, and QD. So the first step is to go ahead and draw the forces acting on charge B. So I'm going to redraw them here just since there are so many things over there. So we're going to have a force between these 2 charges, right? These are opposite charges, so they're going to be attracted to each other. So this one would be pulled to the right, A would be pulled to the right, B would be pulled to the left. This problem is only asking us for the forces on B. So this would be F, let's call it FAB, the force from charge A acting on charge B. And then for C here, we have that they're like charges, so they would repel each other. So charge B would feel a repelling force this way. This would be the force from charge C acting on charge B. And then between D and B, between these 2 charges, they would be attracted to each other because they're opposites. So charge B would be attracted to charge D, so that would be FDB. So we have 3 charges acting on this 3 forces acting on this charge. So the way to do this is to separate the x and y direction of each force and then find the resultant force. So what I'm going to do, before I do that, I'm going to go ahead and calculate the magnitude of each force. So FAB, the amount of this force is going to be the exact same amount of force DB, because it's between charges AB and charges BD. They have the same respective charges, and they're both 1 meter apart from each other. So we don't have to calculate it twice. We can just say FAB equals FDB. And that's going to be K QA QB over R squared. Again, you could use charge A or charge D. They're both the same exact charge. And we're just using the magnitudes of the charge, so we can find the magnitude of this force. So all we have to plug in here is Coulomb's constant, 8.99 times 10 to the 9. And then I'm going to go ahead and plug in charge A, which is 0.35, and in charge B, which is 1. So we have 8.99 times 10 to the 9 times 0.35 times 1 divided by 1 squared. So the answer I got for those 2 forces is 3.15 times 10 to the 9 newtons. And then I'm going to find the magnitude of force CB here, the force between these 2. So for this one, again, I'm going to put in the charges and the distance. The only difference is that charge C is different from charge A, and the distance is also different. So K, charge C, charge B over R squared. So what is the distance between them? This time it's not 1 meter because this is how far away these two charges are. So this, you can see that there's a right triangle here. This is 1, this is 1. So Pythagorean theorem says it's square root of 2 for the hypotenuse. So you either remember this as a 1, 1 square root of 2 triangle, or you go ahead and find side C as the square root of a squared plus b squared, where is the square root of 1 squared plus 1 squared, since a and b are these sides. So that's how you get square root of 2 for the hypotenuse. So when you're plugging into numbers here, we're going to have 8.99 times 10 to the 9. The charges are both 1 coulomb. The distance between them is square root of 2, but then we're going to square that. So really, we're just going to have a 2 in the denominator. And so basically, we're just going to have half of Coulomb's constant as our answer, 4.495 times 10 to the 9. So once we have the magnitudes of the forces, then we need to find the x and y component of each one. So what I like to do is separate the x and y directions. And I have 3 forces, so I need the x and y components of each one. So I need FABX, FCBX, and FDBX. And then I need all the y components, FABY, FCBY, and FDBY. Luckily, these don't take too long to find because a lot of them are the same because we have symmetry with the charges here. So AB is to the left. It's purely horizontal, so it has that whole value, but it's negative because it's going to the left. Negative 3.15 times 10 to the 9. Again, AB is to the left. It does not have a y component, so that would be 0. And let's go ahead and do DB first, just because DB is straight down. So DB does not have an x component. It's all in the y direction. It's negative 3.15 times 10 to the 9. And then we just need the x and the y components of the CB force. So for this force over here, again, which is the force acting this way, this is FCB here, then we need to know this angle here, theta, so that we can find the x and the y components. These are the x and the y components of this force. So, because the sides are the same for this triangle, that means that this angle here is 45 degrees. So that means that this angle right here is the same angle, corresponding angles, so this one is also 45 degrees. So I'll just redraw CB over here. So that means if we're finding FCBX here and FCBY here, and we have an angle of 45 degrees here, and this is FCB over here, then FCBX would be adjacent to that angle, and it would be FCB times cosine of 45. FCBY would be opposite, so it would be FCB sine of 45 degrees. And luckily for our calculations, cosine of 45 and sine of 45 is the same number. So when I plugged in FCB cosine of 45, I got 3.18 times 10 to the 9. And it's positive because it's going to the right. And when I do the sign for this one, this is the FCB. Didn't leave us much room for this example. FCB sine of theta. Same value, positive as well. 3.18 times 10 to the 9 newtons. So that's the first step, is to find the x and y components of each force, and then go ahead and add all the x components together. And I got 3.19 times 10 to the 7 when I did this. And I get the exact same thing for the y force when I add up all these y forces. 3.19 times 10 to the 7. So this is the x component of the total force. This is the y component of the total force. So to find the total force, all I need to do is realize that, well, Fx is the total force this way, Fy is the total force this way. So that means that the total force must be going this way, because these are the two components of the total force. So to find the total force, I use the Pythagorean theorem. And when I did that, I got 4.52 times 10 to the 7. So I do have a typo in all of these answers, which I will have announced in class. But that is the final force, it's the magnitude. We haven't found a direction, it didn't ask us to find this angle here, but that is the magnitude of the force. So just to recap, because this looks a little bit messy, the first step was to find all the forces acting on that one charge. The second step was to find the actual magnitude, the amount of each of these forces using Coulomb's law. The third step is to find the x and y components of each of these forces. And the last step is to put those x and y components together to find the total force. So step 1, step 2, step 3, and step 4 right here. Over here was just a little bit of scratch work to help us find the components and to find distances and things like that.